In this video, we're going to look at correlation analysis. A correlation analysis is used to examine the dependence of two variables on each other. We're going to start with a built-in data frame in R called iris, so we can simply load that with the command shown, and you'll see that the iris data frame now appears up here in the global environment window under values. So let's take a look at the structure of iris using the stir command. And what we can see is that there are 5 different columns of data: sepal length, sepal width, petal length, petal width. All of those are features of the flower of an iris. And then we have a factor variable, species, which has 3 levels, and they correspond to the 3 species of iris: iris setosa, iris versicolor, and iris virginica. Let's take a look at the first few rows of data with the head command. And we can see the 4 rows of the morphological data there, and then the classification or factor variable on the right. Now, to do a correlation analysis, the variables that you need to correlate need to be in separate columns. So our data frame is set up in just the right fashion for that. There are ways to separate data into multiple columns if you have long-form data, but we're all set in this particular example because the data are in the form that's appropriate for a correlation analysis. And the analysis itself is really quite simple. We just call the function cor, C-O-R, and then we just give the 2 columns that we are interested in analyzing. So we have iris, and we'll just do sepal width, and we'll do iris petal width. And we can see that we have a correlation coefficient down below, which is a minus number. What that actually means is that as the value of sepal width goes up, the value of petal width is going to go down. So there's a negative correlation between the 2. However, all we have there is our correlation coefficient, which is designated in statistics as R, little r. But we don't really know whether that is statistically significant or not. So to test whether or not this is a statistically significant relationship, we use the core test function. And rather than retyping this line, I'm just going to add the dot test right there. And now when we run that line of code, we get a lot more information. We get the correlation coefficient repeated, so you can see that's down here at the bottom. But we can also see what the p-value is, and this p-value is a very small number. So this indicates that there is, in fact, a significant correlation between petal width and sepal width. It's possible to do multiple correlations at once, and in the iris data frame, as we saw, there were 4 numeric variables. If we try to do the correlation on all of the columns, we're going to see that X must be numeric, and so the problem there is we have the species column. So what we can do is just to do cor iris, and I'm going to use the subset command. So I'm going to take all the rows, so I'm going to put nothing to start with, and then a comma, and then I just want the first 4 columns. And when I do that, then I get this nice matrix here. So I've got the correlations between sepal length, sepal width, sepal length, petal length, and so forth. They're all possible combinations, and actually they're repeated symmetrically across the diagonal, which is each variable with itself. So that's an easy way to get a whole bunch of correlation coefficients at once. The problem here is that we don't know which are significant and which are not. So to figure out the statistical significance, you'll need to test each one of those with the core test test. Some of them are very high, and like this one here, and so you would have a very good idea that that would be a significant relationship. And some are really pretty low, like sepal width and sepal length, and that might be worth testing just to make sure that in fact it is not statistically significant. So correlation analysis is really pretty straightforward to do. Now sometimes we run into problems in doing analyses in R where there are missing values. What we're going to do is call up a separate data frame here. It's built into R, called the air quality data frame. And let's do a summary on air quality. So what we can see is that there's 6 columns of environmental data, or 4 of environmental data: ozone, solar radiation, wind, and temperature, and then a month column and a day column, both expressed numerically. The problem that we have here is that ozone has 37 missing values, the NAs, and solar radiation has 7 missing values. So that's going to pose a problem. Since all of these are numeric, we could do a correlation matrix on the entire data frame. Doesn't really make a whole lot of sense to correlate the month value and the day value, but just for our purposes we will let that go. So what we're going to do is to just do core, and we're going to say calculate all the pairwise comparisons of these environmental variables. And when we do that, we see that we get a whole lot of NA values here because they were missing values. Well, it turns out that there's an easy way around that. We just add this particular phrase here to our command, use equals complete. So it's going to take away all of the rows that have NAs. And now we have all of our correlation coefficients there.